Welcome to Ask and Learn.
In this problem, we're given the potential energy function as a distance between two atoms in a diatomic molecule, and we have a few different questions about the potential energy, minima, maxima, zeros, the force on the molecule, on the atoms in the molecule, and the motion of the atoms. So some concepts to use in this problem, we need to keep in mind when do minima or maxima, extrema occur, and that will be when the first derivative of a function is equal to 0. When we're thinking about the force, the relationship between force and potential energy, we can use the relationship force is equal to negative the derivative of potential energy with respect to position. When we're thinking about total energy, we want to think about kinetic plus potential, E equals U plus K. And we want to keep in mind this function and how it relates to the physical context. So what values make sense for what's actually happening in reality. And so our function is U of R, so potential energy as a function of R, the distance between these two atoms in this molecule, and it's equal to minus A over R to the 6th plus B over R to the 12th. And so we'll do some basic looking at extrema, zeros and minima and maxima of the function. Then we can look at a graph to verify and to see that that makes sense. And let's see, part A is asking us what values of R do we have a minima or maxima for? So for this, we just want to, again, so to find minimum and maximum values, we just need to look for the points where the derivative equals to 0. So where does du, dr equal to 0? And so first derivative of our function u of r is going to give us a 6a over r to the 7th minus 12b over r to the 13th. So we want that to equal 0. And if we solve that, we will find that occurs at r equals the 6th root of 2b over a. So this could be a positive or a negative, and we could have extrema at either point, but we cannot have an r less than 0. That would mean our atoms have less than negative distance between them, which doesn't make physical sense. So we'll be looking, so we have an extrema at this point. So at this point, usually at this point, it's good to look at a graph of our function. So if we insert that, and resize that a little bit. Okay, so here's our graph. And so we can see we have a minima here, and this is for B. So this is a graph of U of R for B and A both equal to 1. So B and R are just physical constants describing the particular molecule. So we see we've got that at the 6th root of 2, we're going to have a minimum. And our U of R is just going to be increasing as we unbounded as we get closer to 0, right? So we're going to have a minimum right here at the point R equals the sixth root of 2b over a, and the value of u would be a maximum at R equals 0, although we won't reach that in this graph. So our u minimum is going to occur at the sixth root of 2b over a, and our maximum would occur at R equal to 0. Right. And then part B asks us where are the zeros for, where's an R for, where does U of R equal 0? And just looking at the graph, we can see that that occurs at R equal to 1 for this A and B. So let's solve that. And so that would just, that's pretty simple. We'll just say A over R to the 6th equals B over R to the 12th, right? And from there we get our solution for this. R is the 6th root of B over A, right? And so, and we can verify that with our graph. When B and A are equal to 1, that 6th root will be 1, right? So that will be our part B. Okay, and part C, it asks us to plot the graph. And so yeah, let's just take a look at this graph. So we'll see that it has a horizontal asymptote at u equal to 0. So as our separation increases, our potential energy approaches 0. And so it has that local minimum, well, and also global minimum at R equal to that 6th root. Okay, now part D is asking us to describe the motion of one atom in terms of energy. So we want to keep in mind here that energy equals to potential plus kinetic. So we're looking at potential. So we can draw a total energy graph and then draw some conclusions about what kinetic energy will be. So if our potential energy, or our total energy, that is less than 0, we can look at it like this. So let's say this blue line here, I'll say E1, is less than 0. So our kinetic energy can never go, we can't have negative kinetic energy. So we can't go above this line. So if this is our total energy is equal to E1, we have to move back and forth somewhere in this valley between these 2 points. So this atom is going to oscillate back and forth somewhere in between here, right? So it will be a bounded oscillatory motion. And then if we have our E greater than 0, let's say this was our potential energy, E2. Now our kinetic energy is going to be, we're always going to have some, as we go to the right on this graph here, we can't go to the left of this point because then we would have negative kinetic energy. But anywhere to the right of here, we'll have positive kinetic energy. So our atom is going to continually have some positive kinetic energy. So it's going to continue to have a positive velocity, and it's going to continue to move, right? So we can say that for this, if RE is less than 0, and that would be, as example, our point E1, so we'll have our bounded oscillatory motion. And if RE is greater than 0, as in our point E2, we'll have unbounded motion. Okay, part E asks us if for what values of R are we going to get an F greater than 0, F equal to 0, and F less than 0. Okay, so we want to keep in mind that the relationship between force and potential energy. So we'll say force is negative the derivative of potential energy. So in this case, F equals to minus du dr. And so looking at this graph, we can just look at the slope. So we see anywhere to the left of this minimum, our slope of u is negative. So that means F will be greater than 0, right? So F greater than 0 means that our slope of u is less than 0. For F equal to 0, we want that slope of u to be equal to 0. That's going to occur at that minimum point. And for an F less than 0, we will want the slope of u to be greater than 0. Right? And so that's going to occur anywhere to the right of our minimum point. Okay, and we found that minimum point in part A. It was the 6th root of 2b over a. So we're going to have a positive force for our less than that 6th root of 2b over a. We'll have a 0 force for R exactly equal to that 6th root of 2b over a. And we'll have a negative force for R greater than that 6th root point. Okay, so that will be our part E. And then part F is just asking us to find a function for f of r. Right, and so this one we simply say an expression for f is minus the derivative of u. And so we've got our u was minus a over r to the 6th plus b over r to the 12th. So just the first derivative of that function. And we'll get a 12b over r to the 13th minus 6a over r to the 7th. And that will be our answer for part F.